All right, so our speaker today is Maarten Goesten. He is an old friend and colleague. He started out from the Delft University of Technology in Netherlands. He did the bachelor's degree and PhD there, PhD in chemical engineering. And then he moved to Eindhoven University of Technology, also in Netherlands, right?
Yeah.
And postdoc there from 2014 to 2016, and then another postdoc at Cornell University in the US. That's where he and I had some overlap, the 3 years overlap there. Then he continued with another postdoc at the KAUST from 2019 to 2021. Afterwards, he got a assistant professor position at Aarhus University in Denmark. Okay, that's where he is now. He was originally an experimentalist, but he turned into a theoretician, and now he does both. He is good at translating physics language to chemists and the vice versa. Okay, in the field of solid-state physics, material science, theoretical chemistry, mathematical crystallography. Okay. And for today's talk, he told me that he wanted his talk to be pedagogical, so he welcomes interruptions, questions, comments, and anytime during the talk. So feel free to ask questions. Okay. So Maarten, please.
Thank you, Bo, and thank you for this invitation. This is one of the most beautiful cities I've visited. So I actually have a very strong family connection in a region not so far from here, just across the Pyrenees, called Bigorre. And I was in fact baptized in this church here in a village called Visquer. But in the language below is Gascon, Bigourdan even, which is a sub-language of Gascon, which is a sub-language of Occitan. And there's a rich history there. So actually these villages, up to 50% of the people are actually of Spanish descent because they came flying across the Pyrenees, fleeing across the Pyrenees during the times of Franco. And because of that, you actually find a lot of interest in Basque culture also in that region. And about 15 years ago, one summer, I studied Basque. It's unfortunately, I forgot most, but it's very interesting to be here. So today's talk will be, as Bo indicated, very interdisciplinary. I will start with a bit of mathematics, but eventually I'll end up with something very chemical and actually very much oriented on crystallography and structure. So this is what is the meaning of the word tecton? Because molecular tectonics, you may wonder what it means, but just like me and Bo and some people in the Zoom audience today, we were in the group of Roald Hoffmann, and this guy here, James West, also was an undergraduate in the group of Roald Hoffmann. And in the early 90s, he developed a form of chemistry, which he called molecular tectonics, which later is pretty much universally agreed on by most now, gave rise to the large field of metal organic frameworks. And that's the topic that I did my PhD on, mainly experimentally. A tecton is nothing else but a molecular building block which has specific geometric features and chemical features, chemical bonding properties. And when you put that tecton in an appropriate solution, it will self-assemble into a crystal with predictive structural and physical properties. That's the concept that we move to. I will rhyme that today with some considerations. The main considerations that I will go through involve representation theory, which is my specialism, has been my specialism the past few years. But we will make a strong connection to something people around here are also good at, which is the field of topological materials. And this is an old quote from the end of the 1940s by Georgi Gamow, who wrote back then that number theory and topology back then were the only two disciplines not involved or not implemented or embedded into physics. Now we know that that's not the case, and we will touch upon that in a structural and chemical way today. So the first slides are, I will present some considerations regarding group theory and symmetry. So just to rehearse with everyone the definition of a group. So we are a group of people here, but we are not a group in the mathematical sense, because if I combine Bo with one of his students, we don't get another member of the group, which is a mathematical requirement for a group. So what you have, a group is a collection, is a set of objects with added to that usually composition. And if you compose two elements of a group, you get another element of a group. So there is the closure property in the axioms. Another requirement is that you've got an identity element, which returns the original object. And the third one relates to that you have an inverse element, that if you put an element times its inverse, compose an element times its inverse element, you actually obtain an element which is the same as the identity element. And the last one is that it's associative. So AB times C is the same as A times BC. So simple example of a group is just a permutation of three numbers. So there are 6 ways that you can rearrange the numbers 1, 2, and 3. You can quickly verify that this set of linear mappings satisfies all these criteria. Geometrically, for us as chemists, we'd like to show what happens, and what we can do is we can assign 1, 2, and 3 to the corners of a triangle. So this triangle will come back also in terms of a molecule. And what you see here is that every of these mappings actually represents a symmetry operation. So this is what we call the identity operation. So it returns the same triangle. This one gives you a reflection, this one another reflection, and here we have 2 rotations. So what we say is that the permutation group P3 is isomorphic to the 2-dimensional point group B3. So a point group is a group in which the symmetry operation leaves one point fixed. That's the difference between a point group and a space group. We'll get into that. So what we want to do mathematically, and that's actually the extension, so the definition of representation theory is the study of the ways groups act on a vector space. So in order to do representation theory, and actually in order to understand the topology of materials, you need to be aware of the vector space. So when we look at the geometry of molecules, then we have a 2-dimensional real vector space over a real field R, which we can define through 2 basis vectors, 0, 1, and 1, 0. That just means that any point in these 2 dimensions can be written as some sort of linear combination of these 2 basis vectors. Yeah.
There's an error in your slide. Seeing this correctly.
Which
Second
one?
row.
Yeah. Should be 2 on the top and 3 on the below. On the left.
And the
one.
second
Yeah.
column.
This one.
Yeah.
Below. Yeah.
Ah, yeah, you're right. Yeah, this one is actually the identity. Yeah, thank you for pointing that out. Yeah, so what we do when we represent these symmetry operations, we have these symmetry operations, what we usually call them is abstract group elements. So when we have defined a vector space, so we define a vector space through 2 basis vectors, then we can assign a matrix representation to each symmetry operation. So that's what we do here. That's the basis of representation theory. Now, here's a little bit of mathematics that I want to go through, because we will end up with Bloch's theorem and the theory of space groups in a moment. So the mathematical way of actually describing and defining symmetry operations is through the definition of the general linear group, which is quite an abstract object, but it's the collection. So if you look at the general linear group over an n-dimensional vector space, so previously we were looking at a 2-dimensional vector space, then you're looking at all the collection of n by n matrices, all n by n matrices that are invertible. Yeah, so the determinant is not equal to 0. If you have a singular matrix, it's not invertible. It cannot be a member of the element of the group, of a group, in fact. Now, when we have the general linear group defined, what we then define as a symmetry preserving operation, mathematically, also in computer science, is an isometry. So this is a distance preserving mapping given here by the norm. So what we say is that G in this case is a linear group element and V and W are vectors. So what you say here is that the dot product is preserved. Now, what we know is that the dot product commutes. You can just work that out quite simply. And what you obtain is that for isometries, so symmetry preserving operations, the matrix representation, so what I define as a matrix representation is rho of G. So if G is a symmetry operation, then rho G is the matrix representation of that symmetry operation. If you just substitute this into the dot product property, then you find out that the matrix representation of an isometry, the transpose of that matrix representation, must be equivalent to its inverse. Okay? So from that, you can, from that general linear group, which is very abstract, you can define the orthogonal group, which is defined over a real field. And actually all molecular point groups in n dimensions, they are subgroups of this orthogonal group. So the orthogonal group, you take the collection of all invertible n by n matrices, and then you filter out those for which the transpose is equal to the inverse, because those matrices represent isometries. Another property, norm-preserving property that is well known to be true, is that if you have an orthogonal operator and we have an eigenvector and eigenvalues, then we can quite simply show that the absolute value of those eigenvalues must be equal to 1. So if we are working with a real field, that means that the eigenvalues are either 1 or -1 when we work with a real field. If we work with a complex field, so we'll go into that a little bit, then this becomes the unitary group. Yeah, we just change R here into C. Then the eigenvalues lie on the unit complex plane. Okay, so e to the power I phi. This is important to remember. Okay, so this is the absolute value of a one-dimensional representation of an isometry. Okay, now the determinant of such an orthogonal operator is nothing else but the product of the eigenvalues. So if we work with geometry, real field, we know that eigenvalues are either 1 or -1, means that the determinant is either 1 or -1. So there are actually only 2 types of symmetry operations that we distinguish in that way. So rotations, as I will show, they have a determinant of 1, an identity operation also. Reflections, and also improper reflections, they have a determinant of -1. All clear? So the geometry, obviously, this is just the domain of what we are interested in. Wave functions, they live in a different vector space. That's Hilbert space. Now, if you look fundamentally at Hilbert space and the original mathematical context, it's actually an infinite dimensional vector space, but in our calculations and our approach, we actually never approach it as an infinite dimensional vector space. So what we do is that we have certain basis functions, and we describe any wave function in terms of those basis functions. Take a sip. So these can be plane waves, right? So you actually most of the time I would use plane waves, then you get a very large matrix. But for topological considerations, group theoretical considerations, it's better to use localized functions. So you can obtain them by taking the inverse Fourier transform of plane waves, then you get Wannier functions, which we use a lot, or you can actually use an atom-centered orbitals from which you describe the wave function. So if we take, for instance, the trihydrogen cation, which is a molecule that is suspected to be very, very pervasive in space, 2 electrons and 3 basis functions, then we just describe the 3 molecular orbitals as linear combinations of these basis functions. Chemists are very proficient in this, and they know that they know how to derive the irreducible representations of the wave function here. And actually, we have a 2-electron system, so this is a stable molecule, we would predict. And we actually rank the energy of the orbital, so this is another important consideration. The simplest way to analyze using pen and paper the energy of these molecular orbitals is by counting the number of nodes. So here we have 0 nodes, here we have 1 node vertically placed, and here a horizontal node. All right. So, I mean, sometimes I get this question. This is, for instance, computer scientists may ask this, I've noticed, but the molecule is, of course, actually never really in that precise geometry. So it kind of oscillates around it, but because it oscillates around that fixed geometry, this works. This theory, molecular orbital theory, has worked so well that 4 Nobel Prizes have directly derived from it, and one of those is actually by Roald Hoffmann. So this is well-established theoretical chemistry, and this is molecular chemistry. What I want to do now is to show what happens when we move from molecules to solids, because that's where things get very interesting. So if I take this raccoon as a simple object with by itself no symmetry, so this shadow has a function, then as I just showed that if we have a matrix representation that describes the operation over a vector space, then we can distinguish just between 2 types: rotation, reflection, and improper reflection. So from the orthogonal group, which contains all those symmetry operations, all the 32 crystallographic point groups, they are subgroups of the orthogonal group. There are some more molecular point groups than crystallographic point groups, because there is something called the crystallographic restriction theorem, and you cannot find, for instance, 5- and 7-fold axis, which we know some molecules to have. You cannot find those in crystal structures. So the real number of point groups, actually, funnily enough, to my knowledge, it's actually being debated how many there are. People that look at hypothetical versus real molecules, but it's about 40. So what we have there, so those contain only linear mappings where we keep 1 point fixed. The transition from point groups to space groups is the following. So this is the sites notation, but this is an element of a space group. So what this shows is a linear operation, like a reflection or a rotation, combined with a translation. So this is a translation from one lattice point to a next lattice point. One of the simplest ways to show how this works is by showing the 7 Friese groups that were developed by, or actually described by, the mathematician John Conway. So this is actually the simplest one, which is called the Hop group, which is equal to the translation subgroup, because the only linear group element that you can find is the identity. Okay, but you can also define, so Friese groups, they are defined over 2 dimensions, but then a translation is only allowed to proceed into 1 direction. So if you take the Siddle group, then what you have there is, of course, you also have an identity linear operation, but here you have also a reflection. So for instance, you can generate this raccoon from this one by introducing a reflection and then a translation, okay? Now, what we have here, and this is what is really interesting, we have non-symmorphic space groups. So this is something that has no equivalent in molecules. What you have there is you combine actually the linear point group operation. So in this case, a reflection, this is a glide plane operation. There are two types of non-symmorphic symmetry operations, screw axes and glide plane operations. So what you have here is a fractional translation combined with a symmetry operation. So this raccoon is generated from that one by a half, a translation of a half, and then a reflection, okay? So actually, out of the 230 non-magnetic space groups, 159 are non-symmorphic. So the vast majority is non-symmorphic. One property that is very interesting about non-symmorphic crystals is that they have enforced degeneracies, which is very interesting for topological materials. And also, so diamond is a typical example. The maximum side symmetry, so this is tetrahedral in diamond, is lower than the crystallographic holosymmetric point group symmetry, because the point group of diamond is actually octahedral, which has twice as many elements as tetrahedral. So that's one of the properties of non-symmorphic space groups. So because of these special elements, you actually get 230 space groups, which is considerably more than the molecular point groups that we have. And this actually gives us, from my perspective, much richer chemistry, especially if we can combine this with certain established molecular concepts. So that's very much what this topic is about. Now, what I want to, this is actually what I really would like to convey. So I have shown you a few slides ago that if we have an isometry, that the eigenvalue, the absolute value of the eigenvalue must be 1, right? And if we are doing that over a complex field, so we're looking at wave functions, then the eigenvalue must lie on the unit complex plane. So it's e to the power I phi. In physics, this is called the U1 gauge theory. Electromagnetism, for instance, is a U1 gauge theory. But this gives immediately rise to Bloch's theorem, because there is a very important theorem, one of the most important in representation theory, namely Schur's lemma. And Schur's lemma will say that if you have an abelian operator, so an operator which commutes, and clearly, if we take a translation, let's say we go 4 raccoons to the right, and then 2 to the left, that's the same as if we do first 2 to the left, and then 4 to the right. That's clear, right? So clearly those translation operations, they commute. Schur's lemma states that if you have a commuting operator, it must be one-dimensional, which is a mathematical way of saying that it is a scalar. Okay, so that means that the representation of the translation subgroup, so the representation of the translation, is e to the power I phi, where phi is a non-dimensional phase. What we then do is that non-dimensional phase we decompose into the lattice in real space, the lattice vector, and the reciprocal lattice vector in reciprocal space. So together, they describe actually a phase. But when we decompose them, it looks more like this. And actually the 1D chain of hydrogens is serves very well pedagogically. So what we then have is that every lattice vector we can describe as a collection of integers n times a distance between these two lattice points, right? So if we substitute that, so let me just again restate that this gives directly rise to Bloch's theorem, okay? Because Bloch's theorem states that if we have a wave function psi over defined in space R, and we have a lattice translation big large R, so psi R plus large R is the original psi R times a phase vector e to the power I kr. When we substitute that, and we substitute R as NA into the equation, this is what we get. So this is actually the expression. This is a periodic collection of basis functions. Let's call it S orbitals for our purpose now, chi. And what we have here is a domain on the left-hand side. We define a wave function in real space. And here we vary the wave factor in reciprocal space. And this is actually what we plot as a band structure. Okay, so the domain here, and everyone who has worked into this field will very quickly see that this takes the shape of a Fourier transform, right? Because we have real space here, we have reciprocal space there. And just like any Fourier transform, and that's what you will usually see, so that's the relationship between real space and reciprocal space is actually they look like each other. So if we have a one-dimensional real space object, and we also get a one-dimensional reciprocal space object, and this is the domain. To the left is the unit cell, and this is all the collection of wave factors. So any wave function we can define within this one-dimensional Riemann-zone with a domain that goes from minus pi divided by a to pi divided by a. So, and this brings me to one of the most important, I think, for the topology of materials, the most important topic, which is the group of the wave factor. So that's what I will talk about a little bit now. So this is the typical thing that I teach. So here you have a collection of a chain of hydrogen atoms, and this is the wave function for the wave factor k0, and here we have k is pi divided by a, which is the same as minus pi divided by a. Just because e to the power I pi gives you a real number is the same as its own complex conjugate. So that's why that's the same point. However, so what we see here is that actually if we define k to be here, and we are applying inversion, so we can quickly see that a chain of hydrogens has an inversion, is fixed by an inversion operation in real space. If we apply inversion onto that vector, it is mapped back onto this point, which is the same. So what we see here is that at this point, pi divided by a, the group of the wave vector contains the inversion operation. So that is definitely not the case if you move at the interior of the Riemann-zone. If there you have this wave vector here, it is mapped onto the other side of the Riemann-zone, which actually gives you a different point. So the wave function there is the complex conjugate of the wave function here. So those are each other's time reversal partners. So what we see here is that at any point in between these two high symmetry points, inversion operation is not contained in the group of the wave vector. That matters for all these wave functions. Sometimes in the chemistry literature, especially the 80s, 90s, you could see that what chemists sometimes do, because chemists, they don't really like complex numbers. So they take like a linear combination of these two. So if you actually add these two wave functions together, it's an exercise, then you can get rid of the complex parts. But group theoretically, you have introduced inversion and your k vector is not well defined anymore. So from the group and representation theory point of view, that is not correct. And that can also send you into the roots when you look at topological considerations. So it's important to work with complex orbitals, usually. Now, this is well-established picture. So what we get is if we plot the band structure of these of this chain of hydrogens, we get the energy go up as a function in k space. And what we have is that at gamma and x, so at these two, what we call high symmetry points, the wave vector is stabilized by all operations of the point group. So in that case, that is d infinite h, which is the same point group as the nitrogen molecule. But at any point in between, you lose the inversion, as well as some other operations. And then actually the point group becomes C infinite V. So this is very important. And from this group theoretical point of view, the topological nature of the bands arises. And I'll give a brief overview or a brief introduction on how that works. But one of the main typical mechanisms is an avoided crossing. So let's say that we have this chain of s orbitals, which we know goes up in energy. We also then can introduce a set of p orbitals that are translated. And we know that actually for that, the energy goes down. So normally, these two bands, they would cross. But by virtue of the Wigner-van Neumann theorem, it prescribes that two bands, they can only cross in the presence of certain symmetry operations. In this case, S and p orbitals are symmetry. The symmetry is distinguished by parity. So if you lose inversion operation, what actually happens is that within this point group, these two orbitals they obtain the same irreducible representation. So instead of crossing, what you would expect to happen here, this s orbital starts interacting, this s band starts interacting with the top band, and increasingly much p orbital character is transferred into the bottom band. Increasingly much s orbital character is transferred into the top band. What happens is that this band is fully p character on the left and becomes fully s character on the right. Yeah, so the reverse is true here. This is fully s on the left, becomes fully p on the right. So this gives rise, and I don't have time today to go into all the fine details of the topological classification. I've seen some names on the door here, Bernevik, Maya Vernioli, the people who actually are the absolute pioneers in this field who have worked this out. But I will give a simple group theoretical picture of how topology is controlled and why tectonic building units actually are so interesting with respect to those. But with the understanding of this SP mixing process, we can actually distinguish between a trivial gap here on the left and a non-trivial gap here on the right, where in a trivial gap, actually the character of the band remains the same. So for instance, this is an S band, and this is a D band or a P band, for instance. And in this case, we get an avoided crossing, they interact. So actually this starts out as an S band and it's like they cross, but there is an avoided crossing. So that's the difference between trivial and a non-trivial gap. This is an image that I actually like quite a lot from a Japanese paper, which kind of shows the same. So this is the difference. So they're topologically different, okay? And one of the things here is that, so just as much as we cannot deform a ball into the shape of smoothly deform a ball into the shape of a donut without actually tearing up the object or make it go through a transition, so actually creating a hole, we cannot go smoothly from this situation into this situation. And for me, one of the most magical things, and still quite a lot of crystallographers that I work with, some of them, they actually believe that, they barely believe this works at room temperature. But what happens if you have a topological insulator or a material, let's put it simply, with a non-trivial gap? I have a single crystal, and you have then an interface. So you have a surface with air, which we know is a trivial insulator. Because your electronic states, they cannot go smoothly from here into here. They go through a transition. So they go through a gapless region, and actually what you get is topological surface states. So those are metallic gapless states that then emerge on the surface of those single crystals. And that is fully controlled by the energy ordering and the irreducible representations of the wave functions in the band structure. Now, this is what gave rise to the Nobel Prize in physics in 2016. And I think one of the areas in chemistry where this is really taking off is catalysis, where a lot of chemists, physicists, engineers are looking at topological materials to get better electro and photocatalysts. And what they believe is that these topological surface states, they overcome diffusion limitations that have long hampered catalysis, and they lead to drastically improved rates of catalysis. At the same time, the theory prescribes that if you take a topological catalyst and you have a defect on the surface or you modify the surface, that actually the topological states are being preserved. So there's a lot of debate about this, but it's a very interesting field to look at, so the field of topological catalysis. Now, so the theory, and particularly works by Jennifer Cano in the topology field, they describe this very well, group theoretically. So what's essentially this theory prescribes is that you've got the real space representations, which describe your system in real space. And then if you Fourier transform those representations, you get the group of the wave vector in reciprocal space, which then actually determines the topology of the wave function. So to show it using a clear example, I take here the Leap lattice. So there are two lattices that have received particularly much attention, to two-dimensional lattices, the Leap lattice and a Kagome lattice. So my talk today will, after this slide, mainly continue with the Kagome lattice. But the Leap lattice will give you a simple picture of how real space and reciprocal space are connected here. So any crystal structure you can describe as a collection of Wyckoff points, where every different Wyckoff point gives you a different side symmetry. So if you take like the three Wyckoff points here, point 1A is fixed, stabilized, mapped onto itself by all operations of the D4H point group. So this, for instance, this has the point group here, D4H, it contains fourfold rotation and a horizontal reflection plane. So if you take this green point here and you will do a fourfold rotation, you see that you get the same back. Same for this pink point here, which is another Wyckoff position. But if you take, for instance, the black point there, then you see that actually your fourfold rotation, it gives you something different in return. So this is a different Wyckoff position, which actually has locally D2H symmetry. So when you Fourier transform that, and that's why I said the Fourier transform generally looks like the original object to some degree, your Wyckoff positions, they become high symmetry points. And then it's the group of the wave vector which determines the symmetry and the point group of the wave function. So it determines all the operations that map the wave function onto itself. And that's what you get here. You get then in that case gamma, which is always the full point group of the lattice. But we have, for instance, here another point M, where the wave function will also have to be fixed by all the operations of the D4H point group. So what you want with topological quantum chemistry is you want to have control over the orbitals at different Wyckoff positions. This is how you design topological material. This is also not enough, okay? And this is actually very chemical, because if you just only control, let's say we put a p orbital here and an s orbital here. What we also need to control is the energies of the orbitals. So this is real chemistry. Because let's say we have three scenarios. I showed you this avoided crossing here a few slides ago, where this is an s orbital and this turns into a p orbital because we have a non-trivial gap. But we can also have a situation where these two are so far separated in energy that they actually do not cross. So this is a topologically different scenario, okay? And actually the outcome here is pure chemistry, which determines that, chemical bonding property. We can also have a situation where we already have something like a band inversion, or we're looking at heavier elements where you can have a situation where the s orbital actually lies higher in energy than the p orbital. So you don't get any such interaction at all. So what you want, and this is extremely complicated, you want to have some kind of platform where you can control these things. And this is the Kagome lattice, which is even receiving more attention at the moment. A few weeks ago, I was actually at a Kagome meeting. And yeah, the Kagome lattice, what it gives you, that's fully prescribed by symmetry. It gives you a crossing, just like graphene, symmetry protected crossing, protected by six-fold axis, but it also gives you this flat band. So this is sometimes called the topological flat band, which sounds fancy, but the flat dispersion here is chemically very easily understood. So remember that I showed you this triangle, and then we have a horizontal node and a vertical node. So you will always in this hexagonal Brillouin zone find a wave vector, which is orthogonal to the direction of the node. So if you proceed in reciprocal space along that direction, you're not changing any nodal properties of the wave function. So that's why the band stays perfectly flat. This is actually a good student exercise. So what we want is actually a flexible chemical platform from which we can design these things. And this is, long been talked about. Chemists, this is actually a fun article to read by Maarten in 2006, where he writes that design in chemical synthesis, and he means in this case solid state synthesis because it's a solid state chemist. It actually doesn't exist. So we know how to, if you want a pharmaceutical, for instance, then we have a legion of organic chemists that can give you precisely the molecule that you want. But we usually cannot do such a thing with solid state compounds. And this is where molecular tectonics comes in. So this is this collection of papers from the early 90s by James West, where he uses a geometrically well-defined building block. So this is actually a tetrahedral building block. This is old-fashioned notation. So there's a 4 here. So this carbon here actually is a tetrahedral thing. And then it has these hydrogen, what he calls sticky sites. So this molecule actually itself assembles into this porous organic structure, which is not very stable, but it gave rise to what has now become a very well-developed area of chemistry, especially when people started to move from organic into inorganic organic systems, where you have coordination chemistry at play. So you have metal sites, clusters here, interacting with organic units with, again, well-defined geometric properties. So typically they talk about connectivities. This has a connectivity of 3. This is tetrahedral. This is D4H. And there are like these tabula that you can use, which do not always work, I can guarantee you, but they offer a better platform than we have had before. One other thing that is great about them is that they are porous. So whenever there will be some time today, I will show you some very preliminary results of something. But what we can do with porous space is that we can actually post-functionalize it. So we can first make the MOF, or actually we can use a ligand, a building block which contains a specific functionality, and then we can self-assemble the system. Now, if you look at the Lieb lattice and the Kagome lattice, due to some fantastic chemists, we actually have synthetically available metal organic frameworks that will give you these space groups and all the operations and all the symmetries that we need. So I will talk a little bit in a moment about this metal ligand chemical bond, because to chemists, this is an unusual metal organic framework. So typical metal organic framework, you have something like terephthalic acid. You lose the proton and then you get a metal oxygen bond. You don't get a metal that way, right? So this is actually a conjugated system with induced diradical character. So that's what I will talk about in a moment. These systems are great. So what we can already do is that we can tune the pore size using actually ligands that will symmetrically give you the same. So this is a 4-ring, triphenylene, they call this. And this is just hexamino benzene. So they have the same geometric properties, but you get a different pore size, and we can play around with that. So this is important. We can change the metals. So they have been made for quite a lot of metals already. And what is important too is that this X, this is the ligand binding side. We can use oxygen, NH, so this is an isoelectronic, okay, 6 electrons, and sulfur. Much of this has been done by a collaborator, Mircea Dinka. He actually moved to Princeton. very recently, and he developed the large batch of these frameworks. So there are a couple of research groups here that have paved the way. Now, let's move to that metal-ligand bond, because this is where the interaction between chemistry and physics becomes really interesting. So if we take now the simplest molecular complex, this is well cited by Dinka, this is chemistry from the 1990s, and the theory is very much developed by Frank Neese, who is developer of the ORCA program, and he's now director of the Max Planck Institute. So this is diradical theory. So what happens here, and remember the irreducible representations here, is that we have these two interacting ligands interacting with a divalent metal. What happens here is that we get a small gap opening up between the B1U and the B2G irreducible representations. So that gap is predominantly controlled by an antibonding interaction with a metal d orbital. That is happening only for this representation here, and that lifts up the level. What happens here is that if you just do DFT, single particle molecular orbital theory, you just put these two electrons in the B1U level, right? But what happens is that in the real situation, a degree of diradical character mixes in. So this is a case of what in physics is called strong correlation, in chemistry, static correlation. But what density functional theory does is it produces a so-called broken symmetry wave function, broken symmetry solution. So it will put one spin on the right-hand, predominantly on the right-hand side of the ligand, and then the other spin on the left-hand side of the ligand. So group theory will tell you that this is not a proper solution to the Schrödinger equation, because such a wave function is not stabilized by all operations of the point group. What you have here is that if you have 0%, so what usually how we define it, if you have 0% diradical character, it means that none of that is happening. You get a perfectly anti-ferromagnetically coupled quantum state here with the two electrons in this orbital. 100% diradical means full spatial spin separation. But the real, so if you look at the real group theoretically correct wave function, you actually have to do wave function theory. So what happens in the real situation is that just a simplest possible case of two interacting electrons is that this wave function here with spin up on the left-hand side and spin down on the right-hand side, that determines 50% of the total wave function. And here we have the reverse situation. So in the real many-body wave function, these two wave functions are mixed, and then you obtain the group theoretically correct wave function. Actually, the only way to really define in a physically correct way, and this is all developed by Neese and Malrieux as well, is you need to do wave function theory, and then from the CI coefficients, you can describe a degree of diradical character. Again, where actually the degree of diradical character is inversely proportional to the gap. So that gap between the B1U and B2G orbitals, if that gap becomes very large, you get strong anti-ferromagnetic coupling. We get the normal single particle molecular orbital situation. But if this gap becomes increasingly smaller, then actually the spatial separation becomes larger, and actually the singlet triplet gap also becomes smaller. And what is well-established chemistry is that we can control this. So actually, chemically, this can be easily understood because oxygen is more electronegative than nitrogen, and that's more than sulfur. You get less d orbital character mixing into that upper level, which means it's lifted less. So actually, the oxygen one, if you have oxygen as a ligand binding site, you get the largest degree of diradical character. So this is actually the idea of quantum molecular tectonics. So that's combining this delocalized radical approach with space group theory. And this is a demonstration of the concept where we are now introducing platinum. So at this point, this is a hypothetical MOF, but These complexes have all been synthesized with both palladium and platinum as well. So we believe this is possible. But what we try to do here is that we look at what happens when we introduce strong spin-orbit coupling so that we lock the momentum of these charge carriers onto their spins. Now, this is, again, this is a simple picture on how to derive the crystal orbitals from a basis. So this is actually, if we look at the crystal lattice, so what we're taking here is the Kagome lattice, and then the reciprocal space, the Brimenzon, looks the same, but then is 30 degrees rotated. What you obtain is that actually, so the full point group of the lattice, so the group of the wave vector is D6H at gamma, and then here becomes D2H at M and D3H at K. So mind that the D3H point group, it does not have inversion symmetry in the group, okay? So that means that you necessarily get complex phase factors here. And that's what you get when you work this out in terms of the orbitals. So what I need you to see here is that these two orbitals here, B1U and B2G, and what I do to distinguish between representations, IRAPs of point and space groups, I capitalize the space groups IRAPs. So for the molecules, I have made them small, but these are exactly the same IRAPs as that we had for the molecular case, but now we have periodically translated versions of that. They create a very, very small gap, but this is actually just a 2D system. So this is a single layer system, okay? So this lies too far from the Fermi level to actually play a significant role to our physics or to our material properties. So what do? This is kind of similar to what we were discussing yesterday in the group meeting. So what we have here, we have a sheet and then we have p orbitals, okay? Now we start stacking these p orbitals. We start stacking these sheets. So at gamma, the p orbitals, they are plus minus, plus minus, plus minus, so they are anti-bonding. But when we are moving from gamma to A, so this is actually the crystallographic stacking direction, we are moving from bonding, anti-bonding to bonding. So the p orbitals, they become bonding, and that leads to this large stabilization. So what you get actually in the Kagome lattice when you stack it is that this is a replica sort of the left-hand part, and I will finish this talk with some considerations of this electronic band, because this is a very interesting electronic state, which is also topologically important. But what I need you to see here is that this gamma here, that is the stabilization that we obtain due to the stacking. What happens then is that this shifts the crossing very near the Fermi level. Also, what you can see is that, you can see that here too, because this gap is very small and because this is symmetry protected, this must be necessarily very flat. Now, this is what we obtain. So this is the these are the irreducible representations computed at the scalar relativistic level and the full relativistic level. So this is the analysis that you perform to see if your material is topologically non-trivial. So what you get here is that these two bands, they can cross at the scalar relativistic level, but then when we introduce double groups, so from representation theory, we describe this as spin-full representations. Then we see that a small gap opens up here. And then to determine whether the material is topologically trivial, topologically non-trivial, what you do is you define one global set of occupied bands. Those are in orange, which must be gapped. So only at spin-orbit coupling, actually, these become distinct sets, and then one global set of unoccupied bands. And essentially, so only at the points in the Brimenzon in reciprocal space where the wave vector is mapped onto itself by the inversion operation. These are called time reversal invariant momenta. So those are only points gamma, M, A, and L in our case. Sorry, H in L. Sorry, L in our case. Only in those points we can actually obtain a parity eigenvalue for the bands. And then if you have an odd number of occupied parity eigenvalues, you get a negative delta. you factorize that out, and if you then get -1, you have a strong topological insulator. In our case, this is invariantly a strong topological insulator, but pretty much also due to the interaction with this special band here that I will finish the talk with. So this is what we are working on. Pretty much there is a lot of work to do. So the majority of these frameworks, they are magnetic. So these metalganic frameworks, they have also been made for copper. This is one of the more stable ones. And what we see here is that what happens then is that this crossing that happens at near the Fermi level, it splits up into chiral crossings. Chiral means that this is, let's say, so light blue is spin up and dark blue is spin down. So this crossing here is spin up, spin down, and then this crossing here is spin down, spin up. Yeah, so they are related to each other. So these kind of MOFs, they appear to be well semi-metals. There's still a lot of theory work to be done. And what is very interesting is that I've shown you that we have this leap lattice, we have this Kagome lattice, but Mirchadinka, he recently actually developed these MOFs where you're using a nitrogen-centered ligand here. And that nitrogen-centered ligand here, it breaks inversion symmetry. So you get an inversion-broken Kagome lattice, and if you have no inversion symmetry in your crystal, also space group theory, you will actually have spin splitting away from gamma. So all these things are actually at this moment not very well understood. So if you give me 5 minutes, I will show with you some very preliminary results that we're working on right now. And this is this special band that I showed, which was printed in blue a few slides ago. So that band, this is a Slater type orbital basis set. Okay, so those are like Gaussian functions, they're atomic orbitals, not plane waves. This is double zeta, it means smaller. This is quadruple zeta, it means more functions. What we see here is not only that we have this band which becomes much stabilized, but there's actually a band here which completely vanishes at a smaller basis set here. So the band is absolutely not reproduced. And this is as big as it gets. Quadruple zeta with Slaters is insanely big. We're looking at many, many functions. So that band is actually electride-like. So what we have found is there is actually a band which is known to be there for graphite and also boronitride. And this band is called the interlayer band. So that is a band which is not localized around nuclei, but it's localized in the empty space. So with graphite, you find that actually in between the sheets and a little bit centered in the hexagonal pore that you can find in graphite. So with graphite, this has been experimentally probed to be about 1.1 electron volt below the vacuum level. As I will show you, this one lies much lower in energy. So what we see here is that this is a band where the electron resides in the center of the pore. Crystallographically, it is the Wyckoff 1A position. Because this is behaving like a free electron, you can also recognize it by calculating the representations, because it will always transform +1, so totally symmetric, under all the operations of the point group. So this is work done by an undergraduate student who has done amazing work on this actually, and what we have found, so these are very preliminary images, but we see, for instance, that if we move to larger MOFs, so if we move to this isoreticular system, which is larger than this one, we don't find this pore band. So this pore space is too large. But even if we move to the oxygens here, there is, again, like it's probably at some higher energies, but it's nowhere near as low as we find for here, because here we have, with the nitrogen, we have an inner shell of hydrogens. You see that? So this pore is smaller than the pore here. So actually currently we don't find interesting pore bands for those systems. So when we look at the nitrogen MOFs, okay, the ones where NH is the binding site, this is actually some preliminary results. What we do then is we calculate using many Slater functions, the absolute energy using AMS to get an ionization potential estimate. And then we look at the absolute energy of that pore band. So what we see So most of these MOFs, they are magnetic. Currently we are finishing calculations for platinum and palladium just to add two non-magnetic systems to it. But we see that there appears to be some optimum. We can go as much as almost 4 eV below the vacuum level, which is really considerably lower than anything that people have seen before with these systems. So this actually doesn't tell you how close it is to the Fermi level, because if you have nickel, a chemist will tell you that nickel has more electrons than cobalt, and it's more electrons than nickel has 10 electrons. So actually, in this case, nickel, we find that the pore band lies the closest to the Fermi level. It's very close to becoming occupied. Here, you see that? So one thing that we have been looking at is the application of pressure. So we look what happens. Our theory is that we can maybe get this band occupied if we pressurize this MOF. And these calculations, by the way, they are crazy. So here we can actually, this is very preliminary, but here you can see that because of the IRAP, so the pore band is always totally symmetric. This is AG, and we can actually see that it crosses with another band. But also you need to, despite the fact that these are 39 atom unit cells, so these calculations are very expensive, we need to do 6 by 6 by 16 K-space to get anything close to convergence. So these are very expensive calculations. Here you can see slow convergence, but what we now have obtained, and we are quite confident about that, is that if we are at about 14 GPa, we are able to shift that pore band right, the flat part of that pore band, so it's actually interacting with a band that, to my understanding, is a dz square orbital, which also would be called a topological flat band, according to the physics criterion. But what we see here is that we actually can shift the Fermi level straight onto this electronic singularity that emerges from the flat band region. Yeah, so let me finish with a warning, because I'm an experimentalist. So many of these properties that I have shown you, you need to control the stacking quite well chemically. And this is where there is a big experimental challenge, okay? So these MOFs, they can stack in different ways. They can stack eclipsed, they can stack staggered, they can stack serrated, twisted. Usually electron diffraction is the way to figure that out. But if you have, for instance, if we would lose the 6-fold rotational axis in the Kagome lattice, then you can forget about your crossing at K and at H. So it's very important to control it. People are doing a lot of work on that. So for instance, these MOFs are being explored for quantum computing. This is Xin-Lian Feng group, Max Planck in Dresden, who are the best maybe in the application of these frameworks for those purposes. So they're really doing amazing work. But what you can see is that they enforce a staggered stacking to lower spin lattice relaxation rates. And it's not, you don't always want to have eclipsed stacking. It's not that simple. There are also groups that are showing that you can use some polar alcohols, like just benzene alcohol, to enforce some twistronics. So you can actually twist these or similar structures. Yeah, so this is what we have been working on a lot. These are my two collaborators at Princeton, experimentalists mainly, and a lot here is going on. So MOFs usually very difficult to make single crystals of these MOFs. There's been a lot of work done, so that's now becoming possible. But again, still, I emphasize, it does not mean that for all these MOFs we can control stacking. And yeah, let me finish with this. So I believe that if we are at the, people call it the second quantum age or however, but we are currently at an age where I believe multidisciplinary research is very important. And I think we can truly design new materials using such an approach. And yeah, and in that, we should look at some fundamental mathematics. There's a lot of new possibilities when we actually combine chemistry straight with mathematics and look at structure. I feel there is a big niche there. So that's what I want to finish with. And thank you who are here for the attention.
That was a long talk, but I think quite interesting. Any questions from the audience here, also from the audience online? You can type your questions here in the QA tab. So I have a question about the pore band. That's from the stacking of the sheets. And I noticed that the bandwidth, the dispersion of that band is actually quite large, even larger than those pi bands, in-plane pi band. So why is that? If you can go back to one of your slides showing the bands.
Yeah, you could take this, you mean.
Yeah, so for example, here, the red band, that's the pore band, the bandwidth is, more than 2 EV. But those pi bands between 0.5 and 1.5 EV, the bandwidth is smaller. So why do you think that's okay? Because the pore band is by van der Waals stacking, right? It's not some covalent bond.
No, so if you look at what happens when you go from, so what you see here essentially is that the band is very flat. So this is, you should think of this as just an electron, okay? And it's in this pore, so it's actually kind of tubular. You can see it's like a worm. So what you see is that in the gamma MK gamma direction, you get very kind of flat dispersion. That's because this electron and these electrons, they barely feel each other in this direction. But if you go from gamma to A, so if you go from gamma to A, what you're doing is you move from a system without node.
Yeah, I understand that. I'm not comparing this band with itself along the different direction. I'm comparing with the
pi bands.
The pi band from the skeleton.
Yeah, well, yeah, because you have kind of a single unshielded electron, so you get like a roll nodal plane there. Yeah, your anti-bonding interaction is so what you introduce is very, very strong. Now this actually, it's sort of, yeah, we could think more about that, but it's very similar to what is seen with the interlayer band in graphite. So that one also, it takes off very steeply between gamma and A. And actually, if you plot, so what you can do is you can plot just the free electron dispersion. This has been calculated. So there is a paper in 2005 Nature Physics paper on graphite intercalate superconductors. There they calculate just the free electron dispersion. You will also see that it takes off much stronger and more than the normal molecular orbital-like levels.
Okay.
Free electron dispersion typically will be very strong.
Okay. Another question is, if you go back to your slide on the single sheet, the band of the single sheet, one band you didn't talk about is the valence band, that the top band of the black bands. What is that band?
Yeah, but I'm not sure right now. It's some linear combination. So what I can tell you is that it consists of px or py orbitals, because I can tell you that from the degeneracy here. So these are pz orbitals, right? But I'm actually not. No, it should actually not.
The shape looks like it's a.
No, they're all pz orbitals actually.
Yeah.
Yeah, I'm not sure. This is some sort of. So if you actually zoom out, you will find this pattern replicated 6, 7, 8 times pretty, when you go down the Fermi level, because we have many atoms. So for every orbital we have a band, right?
Yeah. Yeah, because that band is touching the Fermi level, so I was wondering what that band is.
Yeah, but so yeah, that's true. Like if you would synthesize this 2D MOF like that,
yeah,
you would, and there's a lot of calculations have been done on that, then you would kind of get this band structure, which is inherently metallic. You can actually find some MOFs in which the 2D band structure will have a crossing close to the Fermi level. The reason why I'm not so interested in these single layer 2D structures because I know that they're experimentally very difficult to obtain. And also when they obtain them experimentally, usually they grow them on top of a surface.
Yes.
So, and then the surface, the electric field of the surface, it will actually quash all the topological observables that you have. So it's not so interesting. Although recently they had the paper where they did synthesize such a 2D layer and they did some spectroscopies on that.
Okay. All right. So if there's no questions, then
No, nothing from Maarten?
he left. He had to left earlier. Okay. He said he will check out the YouTube recording afterwards.
Okay.
All right. So
So you
let's
can email the questions.
let's thank the speaker again.